Hello, my name is Bernard Kozioziemski. I'm at the Lawrence Livermore National Laboratory, and I'm going to be telling you about the multi-layer Lowy lenses for ICF and HED X-ray imaging. This is work that was done in collaboration with the Advanced Photon Source, Argonne National Laboratory, as well as the National Synchrotron Light Source, Brookhaven National Laboratory. The key benefits of the multi-layer Lowy lenses to ICF imaging are large collection efficiency and an extended X-ray energy range. The multi-layer Lowy lenses can have very short focal lengths compared to other X-ray optics, which enables high collection efficiency. Also, the manufacturing process allows higher aspect ratio than Fresnel zone plates, which enable good diffraction efficiency for X-rays greater than 20 keV. These lenses do have submicron resolution possible, but it does depend on the detector as well as the X-ray bandwidth. The table shows an example of focal lengths and solid angles for the multi-layer Lau lens that was tested in our laboratory. For an X-ray energy of 12 keV, the focal length is expected to be 10 millimeters, and for that 100 micron tall segment, that would correspond to a solid angle of 10 to the minus 4 steradians. At 22 keV, the focal length increases to 17.5 millimeters. At 50 keV, it would be 40 millimeters, and even all the way out to 511 keV, that particular lens element, if it was optimized for the right thickness, would have a focal length of only 410 millimeters. These are very short focal lengths compared to other X-ray optics, such as mirror optics, like a KB mirror, or toroidal imagers, or Wolter optics that we have been considering, which have focal lengths in these ranges of hundreds of millimeters. They're also short compared to the focal lengths that you might find for beryllium lenses, refractive lenses, which are again in the hundreds of millimeter length scales. The drawbacks are that the MLLs have a limited size, 100 microns. It's basically based on the coating time, and are subject to chromatic aberrations. Now, MLLs are diffractive optics. They're similar to zone plates, and they're fabricated in such a way as to allow very high aspect ratios. So the MLLs are coated with a D-spacing gradient that follows the zone plate equation and then cut to the desired thickness. In this particular case, there's a magnetron sputtering source, which is sputtering onto a silicon wafer. The MLL is formed as a series of alternating high absorbing and low absorbing regions. This is coated on an entire wafer. After the coating is done up to the desired thickness, then a section can be cut out of the wafer, which leaves a thin lens element. Thicknesses are typically on the order of few to tens of micron thick. And that thickness is set by the X-ray energy that is desired and in the combination with the focal length of the optic as well. This process allows very high aspect ratios, much higher than can be achieved with zone plates, giving high efficiencies for diffracting X-rays and allowing to get the very high energies while keeping short focal lengths. So the key advantage for the MLLs in our particular application are these higher X-ray energies and high numerical apertures compared to other X-ray optics. For details of the fabrication process and some of the previous work that have been done at synchrotrons, I refer you to the references listed at the bottom of the slide. Now, Livermore has tested one of the MLLs that was fabricated by Brookhaven National Lab and demonstrated focusing of 22 keV X-rays. In this case, the lens was 102 microns tall, and for that lens, it had a focal length of 17.5 millimeters at 22 keV. 22 keV is the X-rays that come out of our polychromatic X-ray source, which in our case is a silver anode, and it had a 20 micron spot size. The layout of our test system was the polychromatic source, There was a pinhole that was placed downstream of the source to limit the region of the X-rays that were illuminating the MLL. And then the X-rays continue on to a detector. The multi-layer Lau lens will absorb some of the X-rays and transmit some of the others straight through, but some of the rays will be diffracted into what we call the first order. In this case, it'll focus to a line. The image at the center shows was acquired in this setup. We see the edge of the pinhole as where the X-rays pass through. We can see the darker rectangular region, which is the MLL segment that has absorbed some of the X-rays. And then down below, outside of the pinhole area, we actually see the rays that have been come to focus that have diffracted from the MLL. The plot on the right shows the spectrally resolved version of that image, where we take a line through the center and measure the X-ray energies that contribute to that spot. And what we see is the bright silver K alpha line in the straight through beam in this region up here. And then down below it, outside the shadow of the pinhole, we see the 22 kV line here. And if you look very carefully, you can actually see that the other X-ray energies don't come to focus, but they are spread out over a larger range. And that's because the lower X-ray energies are diffracted more than the higher energies. We were able to measure the efficiency of this lens and found that it was 9% in the X-ray energy around 20 keV. The efficiency is obtained as the ratio of the total photons in the diffracted beam to that was incident on the lens element. Basically, move the lens out of the way and take a reference scan. The efficiency for a 2D lens, which would be made by taking two lenses and stacking one in the horizontal and one in the vertical region, would then be about 1%, which is lower than we would like. But by comparison, this would make the total throughput comparable to that of existing pinholes, although with better resolution. We do have some ideas for trying to improve the efficiency of the MLL. Some of it comes from just the manufacturing process. Also, it would be possible to improve it by having a larger focal length where the X-rays aren't diffracted quite as strongly. Now, we could use these MLLs by simply co-locating those with pinholes on a standard NIF imagers. The MLLs would work better with line emission backlighters than self-emission due to chromatic aberrations. So one way to make use of these lenses would be have a laser incident on a foil. That foil is placed behind an object to backlight it. Then we have the multi-layer Lau lenses, possibly an array of those, located around 100 millimeters away. We could also have pinholes or zone plates or other optics at this location which are similar size. And then those optics are relaying the image to a detector which is further downstream. This layout is based on a similar layout from Alex Doe, who has published this in Applied Optics just this month in 2002, and the reference here. He did this for zone plates. A similar layout works for the MLLs as well. Now, one advantage of the MLLs is that they have a high numerical aperture, and this enables new imaging and diagnostic possibilities. So for example, you could imagine collimating a point source to do X-ray diffraction. So having a laser onto a wire that makes something like a point source. The short focal length allows us to collect a relatively large fraction of these rays and then direct them parallel through the object, which makes interpretation of X-ray diffraction easier. It's also possible to imagine creating a highly diverging point source from a collimated beam and using for high resolution projection imaging, where the resolution is set by the spot size, and it also would give a big magnification. Additionally, we can just use them as very high energy X-ray imagers outside the realm currently used for X-ray optics. Again, I'll summarize the key benefit of the MLLs to ICF and HED imaging are the large collection efficiency and the ability to extend the X-ray energy range up to relatively high X-ray energies, 50 to even 100 keV. which are currently outside the capabilities of mirror-based imagers. Thank you.